I have a question for Franco. It's about the Airy stuff.
Oh.
So
Okay.
it's more about your exchange with Alan. He made a comment one time about
this long-standing exchange has been going on for 2 years.
Yeah, so I didn't want to go back to try to find the source of this, but he said something that to the effect of he said like Franco conceded that in some situation the universe would have to be like around the Earth at a radius equal to the radius of the globe. Is that ringing any bells?
Yeah, I think I heard him say something like that. No, of course, I never did anything like that. Okay, and no.
Do you know like what he's talking about?
Yeah, I know what he's talking about. I think I know what he's talking about, because he says the fact is this: if you, but that's not anything to do with Airy itself. It's got more to do with aberration itself. With aberration, that's what I was trying to tell him while he was saying these kind of things, because the point is, if you measure aberration, and you measure aberration of many stars, not just one, not just the one that was measured by Airy or by Bradley, but you just take all the data concerning aberration of the stars. They are consistent with the stars changing their velocity relative to Earth in a way that's consistent with the motion, relative motion of the stars relative to the Earth. That the motion, almost circular motion, with the radius of the orbit of the Earth around the Sun. So you have
that would be like one AU, not the radius of
1 AU. Yes, because you just measure basically. If you admit that with aberration, you measure the change in relative velocity between the star and the Earth, then you just see, okay, there's a relative velocity that's now it's just changed in the course of 1 year in one direction by plus or minus 30 kilometers per second, and then but this direction changes. So it's if you say plot the vector velocity as a function of time in 1 year, it makes sort of a circle. And then if you integrate that, it means that in time, it means that the star relative to the Earth, it describes an orbit which is the 1 AU in a radius in 1 year, and they all all the other stars have the same behavior. I mean, the aberration that you measure is consistent with this kind of motion relative to Earth, and of course, all of these would have a different center of their orbit because depending on where they are consistent with a motion like this. This is interpreted by Alan and by others as it would mean that they are at the distance relative to, they all are at the distance relative to the Earth that's comparable to 1 AU, which is not true. It's not that, because in order for you to measure this kind of motion with aberration and not with parallax, just by measuring a velocity using light, using the change in angle of the incoming light, you measure their velocity. You don't measure a change in apparent position due to the actual change in position. You just integrate what you measure, the measurement of velocity. You measure the velocity, you don't measure the position, and then you just integrate it in time, and you find that they would have this kind of, it's consistent with this kind of relative motion. So it's not, in order for it to happen, the distance would have to be much larger than 1 AU, because otherwise,
that's what confused me, because I'd heard that before, but it seems like the depending on how far the star actually is would change the size of it, right?
Yeah,
Or
but
at least the apparent.
no, not just the size of it. It just, of course, if you have a star that's as distant as the sun, of course, it would be as big as the sun, but in the sky. But suppose that it's something else, and it's very much smaller, but it's something that is as distant as the sun. Then as you
Well, I mean the
orbit
size of the orbit or the size of the circle it traces. Like if the further away something is, for it the smaller, the further something
yes.
away it is, and if it still travels at 30 kilometers per second relative to Earth, the further it away
Yes.
it is, the smaller circle it will
Yes,
trace.
of course. It would describe as a circle that's one AU. If the star is many light years away, you wouldn't see it.
Yes, But we see all of them trace the same size, right?
Actually, it's a definition of parsec. It's the one star is 1 parsec away if the parallax due to the motion of the Earth around the sun is the angle. So the angle subtended by 1 AU at 1 parsec distance is 1 arc second. So that's the definition of the distance, and that's the typical distance in which the stars are measured. So it would be very very
smaller the angle. So the smaller the parallax angle, the further.
And but that is parallax, that which is also observed, but it's something different. Aberration, you just measure the relative velocity, but then if you have that the relative velocity is 30 kilometers per second and it goes around and so on. If you just take that and just make the integral over time of that, if you know the velocity of something over time, you can reconstruct its position apart from an integration constant, and then you will find that the relative motion between Earth and this star is in any star is actually a circle of 1 AU, and it's centered somewhere far away, and it's parallel to the ecliptic plane and so on. So it's very hard to explain if not that is what is actually moving relative to all the rest of the stars is the Earth.
And the other problem is, Alan and Shane, they say their contention is that the stars are actually 4,000 miles away, which makes it many times worse. And I wonder if he got mistaken, because when I heard him saying that, and he was couching it as a concession by you, but when he was describing it, I was thinking that feels like a lot bigger of a problem for the geocentric model than it does
No, but it's not true that I never considered that. Of course, what I said is that you measure relative motion, which is something that he always he still hasn't. I hate to say that he hasn't understood, but it's what I think. He hasn't understood the principle. I wouldn't say even of relativity itself. General relativity, not general is too much. Of special relativity, but not even that. Even Newtonian relativity. But just the definition of motion. Just the kinematics. If A is moving relative to B, then B is moving relative to A. And if you measure something like aberration, you just measure relative motion, because in any case, motion is always relative, even without relativity. Motion is relative because you only define motion as displacement as a function of time, but relative to something else. If you don't have anything to compare your position to, you don't know that you're moving. You can't measure any movement. You can't define any movement, and so motion is relative. So what you measure with aberration is relative motion. And then he says that you have that somehow aberration is used to prove that it's actually the Earth moving and not the star, which is in physics
the other way.
But
Right. You're
he
talking
said,
about Alan. Alan says that it proves that the stars
yeah,
move and not the Earth.
yes, but he says that Airy's measurement proves that. But the point is, neither is true. You just prove that there's relative motion, and then the way you interpret it, using dynamics and all the rest, but not aberration itself. Aberration itself just tells you that there's relative motion that changes as a function of time in a very specific way, and then you see that everything is consistent with the fact that the thing that is moving relative to the others, I mean, is the Earth, but in a dynamical way, meaning that you have a sort of inertial frame where the stars are more or less stationary, which is again not completely true. And then you have that the motion of the Earth in one particular inertial frame, which is what we call the sun's frame, is the motion of an orbit of 1 AU in radius and with that velocity. That is a description that fits the data. Well, it fits the data, but it also has a much more convenient and easier explanation of the relative motions, but from the point of view of dynamics, not from the point of view of kinematics, because of course kinematics tells you that if I spin now on my swivel chair where I am sitting right now, I can describe this as me spinning relative to the Earth or the Earth spinning relative to me. Of course, one of the two descriptions is more more, say, it's easier to make. They're both valid, but one of the two is easier to make from the dynamics point of view, where the motion and accelerations are described by forces and so on.
Yeah, that's what I've talked to a few flat earthers, I guess geocentrists, about this in the past couple of weeks, and I'm careful not to say, because sometimes I'll ask if aberration is like a 100% proof that the Earth is moving around the sun. And I usually say that what you just said, which is, well, you can theoretically with anything you could kinematically describe it the other way, but it's weird, you know. To me it's kind of like, I thought this analogy of like you're on a boat and you look out and everything you see, the water, you see mountains in the distance, you see birds flying, and everything you see is like moving up and down. It's oscillating up and down.
Yes.
And you could say, well, and you could say everything out there is moving, and the mountains have to move a lot more to have the same displacement than something close to me. You could say, oh, maybe that's happening, or maybe the boat is just going up and down over some waves. That's kind of the equivalent for me with Aries. So one of them is a much
it is. It is, because not Airy with aberration itself. Now Airy is a different problem. Airy is a problem of what happens when you fill the telescope with water. But it's true, because the point is that one of the two frames, the two objects that are moving one relative to the other, is more, say, inertial than the other. Because if two objects, like you take the Earth, and you take, or yourself on Earth and a star, and they're moving, if they were moving with constant velocity, one relative to the other, then there's no point in saying who is moving relative to who. It absolutely makes no sense in even in dynamics, because we have relativity principle and the fact that all inertial frames are equivalent. So you can always subtract, say, a constant velocity from any motion, and you get exactly the same physics. But the point is that you have this relative velocity between, say, Earth and the stars, and every single star is changing during the course of 1 year. And then you have to say who is which of the frame between the Earth and the rest of and the star is the inertial frame, the one where we can describe physics in a easier way. And of course you would have to, as you say, it's exactly the same thing as you see. You're in a boat and you see everything oscillating up and down. In order to oscillate up and down, you will have to have a harmonic force, an elastic force on everything except you, because in physics, if you have a motion that is accelerated, like a circular motion or a harmonic motion, an oscillating motion, you need to have a force that causes this acceleration. So if you claim that aberration is due to the Earth being an inertial frame and the stars making each of them in an orbit of 1 AU around a different center, and they're all doing it 1 year period, and with the same radius, all parallel to each other, all parallel to the ecliptic plane. It really has no believable dynamic explanation. Of course, kinematically is exactly equivalent, but of course you wouldn't have to explain why the stars are accelerating that way and making circular motions around each a different center and so far away from us, but all motion parallel to us, and so that's the thing. Exactly, your analogy is perfect. Yeah.
The other thing I wanted to ask you, I don't know if anybody else wants to jump into, but so Witsit, we were talking about this, and he brought up. Did I send you the link to his website? Anyway, he's building he's using AI to build a website that shows like how he's trying to overcome the dynamics piece of it using Mach. And so he cited a couple people. I don't know that much about it. One of them was Assis, ASSIS. And supposedly there's a paper that shows, I couldn't tell how far reaching it was, but it sounded like using Mach's principle, it showed how, pseudo forces on Earth like Coriolis could be converted into real forces or whatever through the Machian principle. I was curious if you're familiar with that.
No, but I'm familiar with the kind of mechanisms that people like Witsit use, because they just look for some fringe papers and without understanding them, because and then they just make up a lot of very big words, big concepts that nobody really understands, and then he presents them by speaking very loud, not very loud, very very fast, so that it's very hard to even follow what he says. And I've had discussions with him before, and it's really hard to discuss with people like that, because he's really read a lot, but there are many clues in the discussions I had with him, and things I heard him say that indicate that he really doesn't have the necessary background to understand all that. And the very famous, one of the very first interaction I had with him a couple of years ago when I first stepped into a flat space was about his claim that gravity on the surface of the Earth is actually due to electrostatic field, and he used arguments there that showed that he really does not understand electrostatics and
that's just an ad hom. Good job, Franco.
Oh, hi. No, it's not an atom. It's
Who you guess?
Yeah.
Talking about Whitsitt or Allen or Shane or something?
It's an assessment. Okay, so
Whitsitt.
so I didn't know you were there, but okay, I still think this is a fact. But okay, so I don't want to talk about.
By the way, I talked to him. Funny, I talked to him yesterday. We were talking about
people. So
yeah.
But it's not corrected because it's not correct to talk about people. It's correct to talk about physics.
But I think it's fine. It's fine to say that you, as somebody with experience, if you talk to Whitsitt, he shows some aptitude, but doesn't really fully.
No. But the point is, it's not one of the things. Just to reply to what I was told, it's not. I don't like personally the approach of this kind of discussions, because the approach which is the fallacy hunt, because this is not. I understand this is not the way I was personally brought up in discussing science and discussing physics and doing physics and doing science. I think I've understood from the experience in this couple of years that this is something that is very much rooted in Anglo-Saxon or American, I don't know, maybe also British culture. And it's something that I didn't know that the debate championship or tournaments are normally done in high schools and things like that. So it's a kind of thing that some group of people, some culture does, but it's not habitually. But it's not what is done in international science milieu. I would say I've never heard any. As I say, I've been to conferences, to international conferences in physics and so on, and never heard anyone think something like, "Oh, this is a fallacy. Oh, this is an ad-hom. This is a non sequitur. This is red herring, and so on." It's a kind of type of discussion that is not the way I'm accustomed to and when discussing physics. So I don't want to fall into. I don't want to go down there, and so I don't want to reply by saying, no, this is not this kind of fallacy because this is you're assuming this is a fallacy is a fallacy itself because blah 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 and going down the list and so on, because it's not the way I'm accustomed to physics, and I don't think it's the way it's done. And another aspect of this is that you don't discuss science with just vocal discussions. You need to have equations, data, plots, and things like that.
Yeah. I think it's different. I think the debate, if you went to a high school debate in the US, they're not going to be talking about science topics. They talk about like politics, or it might be the morality of the death penalty, for example, type thing.
Yeah, but but by the way, it's
just bled over into science. I think you have people maybe that have taken philosophy classes, and then they come to this debate and they just do. It's kind of what they're used to.
It's just a funny coincidence that I'm reading in these days. I'm reading for the first time. I never read that before. I'm reading The Shining by Stephen King, and Jack Torrance, the hero, say the villain of the novel, used to teach debate in high school, and had a debate championship. And he had to train. He was a trainer of a debate team. So I say, okay, that's what debates lead to. The Shining.
Yep.
But okay, it was just a joke. But it was a confirmation that it's something that this was written in the 70s, and something that is very deeply rooted in possibly American culture. Here in Italy, I've never heard of anything like that. We don't do that.
Yeah, it's definitely I think probably every high school has a debate team in the US.
Yeah, no, yeah.
It is interesting that you guys don't. But I posted a paper in. This is one of the papers that Witsit's been presenting lately. And I don't know if you've come across Popov's work, but he's the guy. He had a paper a while back about the Neo-Tychonian model. So it's he had a paper where he showed the kinematic equivalence for like the Tychonian model is, I believe it's where the sun and the moon and Mars and Venus orbit the Earth, and then everything else orbits the sun. And then I think he's advanced. So now there's further
the Earth, and I know it's well, it was before Copernicus. It was the sun orbiting the Earth, and then the other planets orbiting the sun. Yeah.
So anyway, I think he's moved on, and he's trying to make a dynamic. So it's like he's moving into the dynamics piece of it. So obviously Witsit's lapping up everything I think they're all preprints, to be honest, but so I was curious if and I think this maybe references the other paper I was talking about.
Yeah, but I don't know. Anyway, I don't know about this, but anyway, the point is, if if you use like general relativity, you say that all general relativity has, which I'm not an expert in, by the way, so I'm not really prepared to discuss this to discuss general relativity in detail, but it claims that all reference frames are equivalent, including accelerating frames. So, but the point, the cost of that is that you have to change the metric of spacetime and so on. And so I think it must be something of that kind. You just adopt a different perspective. You adopt a different frame, and then describe it in a sort of more complicated way, because you know that, for instance, in Newtonian physics, when you use a non-inertial frame, you have to introduce fictitious forces and so on. So if the claim, I don't know, because I've not read these kind of things, and I'm not really, to be honest, I'm not really totally interested in reading them. But if the point is that you have a different description, in which the only thing is that you say, okay, the equations are the same, everything is the same, the predictions are the same, only I interpret the fictitious forces to be real, but the net result is that given the same initial conditions, you get the same results, and you get the same equations for the motion, and you get the same predictions. Then why? Why, if not because you like it better?
It's not really falsifiable or testable.
Yeah, no. If it doesn't, not just the point of being falsifiable or testable, but if it doesn't make any difference in prediction, if for instance, it's like saying, I was discussing on X on the X Twitter with people like Ken about the flat earthers like to oppose Einstein and certain general relativity with Newtonian gravity, and thinking that they're two things that are mutually exclusive, to say something that Alan likes to say. But it's not like that. It's not like that one is one or the other. One is true, the other is false. They're two complementary descriptions. They're two descriptions that are completely equivalent when within some certain limits. And general relativity is wider, meaning that it describes phenomena beyond certain limits, in the relativistic limit, in the cosmological limit, and some other limits where Newtonian physics is different. But for things like an apple falling on Earth, and saying one of the two says that the apple is actually pulled to the surface of the Earth, by a force, and the other one says that the apple is actually following a geodesic path, and it's actually the Earth that is sort of accelerating towards it. There's no point in saying one is true and the other is not, because they predict exactly the same thing. There's two ways of saying the same thing, and it's actually it's not actually choose one or the other, because it's not the point. And so if you have a Machian theory that comes about and describes exactly the same thing with exactly the same situation and doesn't have any different prediction, there's no point. I was sorry, I didn't finish the what I wanted to say earlier, because general relativity, as far as the prediction of what happens on the surface of the Earth for the Artemis trajectory, for the Moon's trajectory, for the trajectory of space travel and so on, is usually it's more than enough. You have that general relativity makes better prediction in some very specific cases, such as very precise timing measurements, such as the GPS and things like this, or effects such as the bending of light and gravitational lensing, or the precession of Mercury, or things like gravitational waves and so on. So it makes predictions which are not there in Newtonian, but in the limits where the two are indistinguishable, there's no need to choose between the two, and usually what one does is to choose Newton because it's easier, and the same. So the only point of deciding which is best is when they make different predictions, and then you compare them and you see what matches what you observe. So if you come up with some other Newtonian view which makes exactly the same prediction as the one we have now, why change? If you come up with different predictions, then okay, we test and we see what is the better description. That's what we do in science.
I gotta jump off at 10, but for me, just like the debate part of it's fun, and I think for people like Whitsitt, they've been saying the kinematic thing and then getting beat up to say, well, there's no dynamic explanation for geocentrism or geocentrism for flat Earth. Basically, this would give them, like, it lets them support the geocentric belief. My take is, if it is equivalent, I'm happy to just concede it. You know what I mean? I don't want to necessarily fight against it, but I do sort of want to understand what the scope of it is, like how how much of our existence is explained by just doing this sort of like moving a frame and just reorganizing the universe sort of thing.
Do you think that just looking at it isolated, just the kinematics of it, is sort of a problem? I mean,
yeah,
most of the things that we do see and measure, there are some dynamics involved.
Yeah, I mean, like, to me, there's problem, just the idea that everything goes around the sun except two of the planets go around Earth. I mean, it just feels very, the heliocentric makes way more sense in my mind, but I don't, if I get into an argument about kinematic equivalence, I have to concede that, but I also have to concede that, I could be the center of the universe and everything is rotating around me. Doesn't make it.
Yeah, I agree. But it's like, another thing is like, well, if the universe is orbiting around us every 24 hours, well, then it must be quite a small universe. Otherwise, the objects would have to move faster than the speed of light.
Yeah, but
that's what I mean. If you go by things isolated, just a tiny part of the whole, yes, you can probably justify quite a lot.
All right, I got to jump off. It's good chatting, Franco.
Okay. But if I may, but so if there's no one else interested in what I'm saying, so probably I'll jump off too. But the point is.
No, go ahead.
Okay.
Yeah, continue.
The point is, one of the things that struck me first time I jumped into this kind of spaces is the dilemma or the fight between two cases, which is geocentric or heliocentric. Like heliocentrism is presented as the modern or the mainstream. Heliocentrism made sense 200 years ago. Now it doesn't make sense. To talk about heliocentric universe, we know that it's not heliocentric. We know that we're moving around the galaxy, and the galaxies are moving themselves, and so there's no point in saying that. At some point, people in Newton's time, they might have discussed whether the sun was the center of the universe, but it's not. We know that it's not, absolutely. So it really makes no sense to talk about heliocentrism now these in the 21st century. That's something that really strikes me, and even let alone the fact that people are still taking as experiments things that were measured 150 years ago, like Airy and things like this. We should probably update a little bit.
Yeah, but I think one of the problems as well in these debates is that the denial of, I mean, let's say the redshift and blue shift of the CMB, which shows that we are moving towards one side of it. Very often in these discussions, what comes up is no. It could be due to something unknown or magic or something like that. That was making it most difficult, if you ask me.
Yeah, and by the way, the first time I heard about this typo measurement in CMB, I was still a student, and I was really shocked because I said, wait, then there is a preferred frame, which is a CMB, and so we are measuring an absolute velocity, which is ours relative to the CMB, and I think that this is in a way true, but I, from the little I know of cosmology and general relativity, I've tried to look up this question because it was really a shock to me because I didn't understand probably general relativity well enough. But I think that the answer to this is that you really have a sort of locally inertial frame determined by the amount of mass in a very large region, and that you can consider in a way the frame in which the CMB, for instance, is locally isotropic. It's something, again, that since I'm not really expert in general relativity, I don't want to discuss in detail because I'm not capable of doing that. But there are ways of explaining this without renouncing general relativity, of course, because otherwise it would have been a shock for everybody. It is not. It was a shock for me because I was ignorant of general relativity and not knowing how to explain this.
If I can get a question in.
Yeah.
You're the gentleman that works at CERN, if I'm not mistaken?
Yes. I'm not paid by CERN, but I am a member of CERN, yes, in the sense that I'm associated to that because I've worked for many years for
nice.
in experiments that are based there.
Nice. Glad to meet you. I'm SC Montreal.
Nice to meet you.
I'm wondering, because I heard you before say about the apple falling.
Yeah.
And you gave 2 examples and you said it doesn't really matter.
Yeah.
So I would like to ask you a question because this comes up a lot.
Oh boy.
With
Oh boy.
Yeah. Oh boy. You can hear the tension in the room already.
Okay.
So now this comes up with the ballers all the time, right? And I asked them like, okay, if let's say on your sphere, right? You have 4 people, North Pole, South Pole, East and West on the equator, and you all drop a phone at the same time, right? Now, how do you figure this could happen if the Earth goes up to meet the phone? Would that not say that the ball has to expand? I'd like to hear your opinion on that.
Yeah, that's the point. That's the point of understanding what these people making this example mean. It's not that simple. I mean, it's not like that. That's why I was in replying to Ken on X. I was saying the fact that people like I was explicitly quoting Brian Cox and these physicists like to go out and explain these concepts which are not easy at all to a wide public, and the risk in that is that some fraction of the wide public might think that that's it. Oh, I've understood what he's saying, so I've understood general relativity, which is absolutely not the case. It's something much more complicated than that. This is a way of explaining it in simple terms, but in order to work out the consequences and in order to understand it properly, one would have to actually study the matter thoroughly. And studying general relativity thoroughly, which is something I have not done, and I'm a professor in physics at university, is something that requires years, and it's something that's really well, it took Einstein himself 10 years in order to understand Riemannian differential geometry in order to develop general relativity. You have to understand that. If you don't understand differential geometry and Riemannian manifolds, you don't understand general relativity, and so it's useless trying to explain it to people who obviously don't have the necessary background, because very few people have the necessary background to understand that. So, but the point is, it's not really accelerating in the way you're saying. It's accelerating in a different way, in the way in a space-time perspective, not a space and time as 2 different things perspective. So in general relativity, if I understood it correctly, because if I understood correctly what Brian Cox was saying when he says something like that, is this. I've heard a video when he says this, and he says that when the apple falls, in the Newtonian point, from the Newtonian point of view, you have that the apple falls because it experiences a force, which is gravitational force, which is proportional to its mass, and so due to Newton's equations, it accelerates downwards with an acceleration which is the force divided by the mass, which is g, little g. From the point of view of general relativity, instead, and then of course, in the Newtonian point of view, then the apple reaches the ground, and when it reaches the ground, it stops falling because the force of gravity is balanced, is cancelled by an upward force, reaction force from the ground. and then the two forces cancel out, and the apple stands still. In the Einsteinian, so in the general relativity point from general relativity
Can I
point of
interrupt you
view.
just for a second for clarity?
Yeah. Yes.
Are you saying in the Newtonian model that it stops when it hits the ground? It stops because the ground is moving up.
No.
In the Newtonian model, are you sure about that?
No. I never said that it's moving up. I said that when it hits the ground, it stops moving the apple because the ground applies a reaction force to the apple, which balances the gravity. This is the reason why you don't fall in a Newtonian point of view. You don't fall because
I thought
when you're sitting on a chair, when you're standing on a scale, you're pushed down by gravity. The scale pushes you up, and the net force is zero on you. You don't move, but the fact that the scale pushes against you is measured by what the scale actually is reading. And this is the Newtonian point of view.
Let me just lay out the.
Okay, but I have to. I don't know if you have a
He's
question.
He's not finished
here,
though, Jeremy. He was halfway. He was halfway through.
Right. I was halfway.
All right, I'll lay out the problem after again. Go ahead.
Okay, so the other point of view is this: in the Galilean, in the Einsteinian point of view, the apple falls. It's not actually falling. When it's free falling, it's actually moving in along a geodesic word line, meaning that it's equivalent to something standing still according to Newton's first law, if no force acting on it. It's in Newton's first law. If no force acts upon something, upon a body, that body preserves its state of motion, meaning that it continues moving in a straight line with a constant velocity, and so on. In Einstein's view, if a body is not subject to any forces, it will not go in a straight line with constant velocity, but it will just follow the generalization of this, which is following a geodesic curve in space-time. And this, in that case, would mean that it's moving downwards toward the center of the Earth, would be. And then the fact that at some point it stops is because the surface of the Earth is applying a force to it and forcing it, when it stopped, to follow a different word line, meaning a curve in 4D space, which is not a geodesic, which means because a point that is standing still on the surface of the Earth is not a geodesic in the curved space-time, and space-time is curved because the Earth is massive, and so it curves space-time. This is in the Einstein point of view, of course. From the Einstein point of view, around the Earth, the space-time is curved, meaning that a point standing still on the surface is not following a geodesic curve, and so it's quote-unquote accelerating. It's doing something that needs a force to be applied on it in order to do that, and the force applied to that is the reaction force, the same as in the previous point of view, the upward force applied by the surface of the Earth. So it's as if the Earth was locally accelerating upward, but this is in a Newtonian point of view. So in a Newtonian point of view, from a Newtonian point of view, if you are accelerating upward in an elevator, you feel pushed downwards. If you're accelerating forward in a car, you feel pushed backward, and so on. And so that's the analogy of saying that the Earth is accelerating towards you. But it's not expanding. The point is that a sphere that is stationary, or a point that is stationary on the surface of the Earth, from the point of view of general relativity, is not following, even if it's stationary, so its coordinate in space and time are not changing. That is not a word line that is geodesic. I know this is not easy to understand because it's a complicated subject, I tell you.
Well, let me just say this and let Jeremy get in after. It's not easy to understand because it's not physically possible. Because if you have 4 points on a globe and they're both moving to meet the object, like you can try to use fancy terms to explain that, but it's just not physically possible if you think about it in reality.
It's true. It's true. But what I'm saying is that they're not moving upwards. The Earth is not expanding. It's just that the fact that it's not expanding, so that the points are not moving. So you take a point, say the North Pole, just to one of those 4 points that you mentioned. You take a point at the North Pole on the ground. The cell phone on the ground on the North Pole is not moving in either description. Its coordinates are not changing with respect to time. So it's not, and the Earth is not expanding. But that trajectory, meaning a flat line in space-time, is not a geodesic. Meaning it's not what a body would follow in absence of forces in the Einsteinian point of view. That's the point. I know it's not easy. It's not something that could be understood very easily, and it's not intuitive. It's not, but it's another way of saying the same thing. But it doesn't say that the Earth is expanding. It's not accelerating in the way that you think it is, that people understand it is. That's why my opinion is that these people should not say these kind of things, because people are bound to misunderstand them, because the vast majority of us has not studied Riemannian differential geometry and does not understand what he's talking about. So it's just, he sounds like a wizard saying very impressive sounding words, and people will say, "Oh wow, he's a genius." But some other will say he's an idiot because he's saying impossible things. And
yeah, that's the camp I fall in. To be honest with you.
Sorry?
I said that's the camp I fall into when I hear stuff like that. It's like it's just physically impossible. Now, maybe they mean something else that I don't understand. Yeah, granted, but yeah.
Because what they mean is very difficult to understand. It's not easy to understand. That's what I'm saying. They say it in words in order to be understood, but the effect is that they're not understood. It's not understandable if you don't know what a geodesic is, if you don't know what we're talking about really mathematically. And what I was going to say to Ken, which I didn't in the end because I made too many reply, is the point is you don't need ordinary. Sorry, I had a slip of an Italian word. You don't need the vast majority, including myself, because I have colleagues and friends of mine who are working as experimental physicists on the detection of gravitational waves in LIGO, Virgo, and so on. And okay for them, and I have cosmologist friends, okay for them, but for me, as an experimental high energy physics, I don't need, that's why I didn't study it, I don't need general relativity. I can do without that. And I don't need to understand it. It would be nice. I would like to. As someday I bought books and I want to do that, but I know that it will take a long time and a long effort to understand it. even from a point of view of a person like me who has had a whole 40 years of study in physics, it's something that requires a lot of effort to understand. And most people don't need, even physicists, do not need that. Leave it to physicists who actually use it. The general relativity, I mean.
Thank you for your answer and for being honest. And I think Jeremy wants to get in.
No, he said he couldn't. He stepped away.
Oh, okay.
I have a quick question to Franco. Franco, I saw this. I saw like multiple videos on YouTube trying to explain, like the curvature of space-time, like saying that the Earth's surface, because it's like because it cannot fall any further than it has, but like time still flows down, that it goes against the flow of time.
I'm not sure.
That's not a.
I'm not sure exactly.
Is that not a good explanation?
I don't know. I'd have to look into it. But again, as I say, I don't feel like I'm the right person to discuss general relativity. I know something about it. I know some general principles. I know what terms are, but I wouldn't be able to discuss it in detail. And that's one of the points that I always make with people like science deniers, and because what they don't understand, many of those, maybe they're in good faith, but in order to understand, especially physics, I don't know about biology or molecular biology or brain surgery or whatever, or geology or other fields of science, but I know about physics because it's my field. In order to understand what I mean, what usually is meant by the people in the field, when we say understanding a subject, it means that we really master the equations. I was sending a private message to Alan, restating this once again. It means that it doesn't mean that you're able to find a proper quote on a paper from 150 years ago and highlight it and think you understand the physics because you've selected a quote from a paper or from a letter that Einstein sent to his cousin. It's different. It's if you understand, you know that you've understood something, a subject in physics, when you can rederive all the equations involved by first principles, and by yourself. You have to do it on with pen and paper, rederive the equations yourself, and then solve problems. If you're not able to solve a problem, then you don't know the subject. And there are many subjects in physics that I feel I don't have a total grip on because I know that I wouldn't be able to solve immediately a problem on that.
Can I ask you a different question?
Hang on a minute. Hang on, Stefan. You use the term science deniers, and that to me, there seems to be an issue here, because if there's something going through natural science with an IV, independent variable, and somebody's testing and repeating something to establish a cause of some observation they've made, that's a bit different. I think most people accept that. I would certainly. Anybody that denies that, I'd be like, they're doing it multiple places. Everybody can do it. They can send it to them. They can test it. Repeatable. That's what it's all about. But when you say science deniers and you're talking about physics, there's all kinds of areas. Theoretical physics, people could deny that because if it's just, say, a mathematical model, then it doesn't necessarily reflect reality, does it? So you could deny quote unquote, couldn't you?
No, because the point of physics is exactly that's one of the objections that I've always had. The mathematics does not. You have to substantiate in reality and so on. No, the point of physics. I don't know about geology. I don't know about microbiology, but physics is precisely making mathematical models of reality. It's that. And then you have a mathematical model, and the point is that the mathematical model needs to have a number of unknown parameters, which is small, relatively small, and then such that you make a number of observations, you adapt that, you measure these parameters, and when you've measured these parameters with a number of observations that is possibly much higher than the number of free parameters, then you check, you have completed the model, and then this model must have the power of being able to predict the result of other tests that you make. So the model needs to have these two characteristics. It needs to be able to describe all of the past observations and present, and needs to be able to predict what you will find if you make an observation in this and this conditions.
Well, we need to be careful with that, though. We need to be careful with that, Franco, because there's all kinds of people predicting things, like in evolution, where they go, "We predicted we'd find this fossil in this place. Look, in the geographic column, it's there."
I'm not talking about evolution. I'm talking about physics.
Listen, I'm telling you about the models that they put into the world, that they've said, look, these are true. The COVID models they did for the UK, for instance, were completely bullshit. Nothing that reflected reality whatsoever. So I'd be very careful about accepting a model where it doesn't have any physical representation whatsoever, no demonstration. Demonstration's important part of physics, at least some physics, right?
So it's like the Higgs boson before they found it, sort of problem.
Yeah.
Is that what you're thinking of? Yeah.
They haven't found it, though. They haven't found it. You are aware of that, Stefan?
Yes, we found it.
No, come on. You found something that you think is that, but the boson wasn't found. You found something that it excited or something, but the Higgs boson itself was not found. The God particle.
Well, then I should give back the thing that I'm holding in my profile picture, which was exactly given to our experiment because we found the Higgs boson. We have to ask. Well, Higgs unfortunately is dead, but he got the Nobel Prize, so we have to give it back, the money back, if you think we haven't found it. We have found it, and we have. By the way, I wasn't if you had asked me in 2010, I was telling everybody that I was convinced we wouldn't find it but it was completely so a whim of mine. I didn't have any reason for saying that because I wasn't actually doing the analysis and trying to make measurements myself. So I said, no, I think it's like supersymmetry. Supersymmetry, we will never find it. But people still searching for it. But the Higgs boson, no, it's really unmistakably there. And we
hold on. If my memory serves me, sorry to interrupt you. Didn't they find something that it decays to, or something related to it, but not exactly that? I'm gonna go and search the paper. I don't remember exactly, but I distinctly remember them saying that it wasn't found. It found something that decays to it that was visible for millisecond or something. Can you speak on that?
You measure the decay products of the Higgs boson. You don't. You see its effect. You see the fact that it decays to something.
So I'm correct. It wasn't the Higgs boson that you detected. It's something that you think it decayed into. So I was correct in that.
No, because it's exactly what is predicted. It's exactly what is predicted to be to do. So if you find something that quacks like a duck, walks like a duck, and so on. So if you have a prediction that if a Higgs boson exists, it is produced at some point. It is produced with certain probability and at certain mass and certain energy, and it decays to this and that according to this angular distribution with this invariant mass and so on. You predict exactly what you would see if it existed, and then you find that it does exactly that. So you found it. You find.
So is there? Sorry, go ahead.
Same for anything else, right? If you measure anything, you don't measure the thing itself. You measure the effect. Even if I'm holding now holding a coffee cup in my hand, what I'm actually feeling is not a coffee cup. Is I'm seeing the image on my retina produced by light hitting first the cup and then the retina, and then sending impulses to my brain, and then I'm feeling it in my hand, feeling some pressure on the nerves on the skin of my fingers, and then the nerves are sending the impulse to my brain, and my brain is elaborating the information and interpreting as if I'm holding a coffee cup in my hand. But who tells me that this is a real coffee cup? It's the same thing. Whenever you measure something, you actually measure the effect of that something on your instrument, whatever it is. Maybe your eyes, your fingers, your scale, your telescope, or whatever.
It's a coffee cup because you've labeled what you're feeling. You labeled what you're feeling and what you're seeing. You've labeled it.
Hold on, Robert. Hold on a second. So you're saying that this decay that they detected, which they attribute to the Higgs boson, you're saying that there's no possible way that it could be something else, and you were mistaken about it.
Oh, there's always a possibility, but that's why we keep measuring it. But that's true for everything. You measure
so
it.
Then, I mean, how certain are you? How certain are you of that it is the Higgs boson, the thing that gives mass to other particles? How certain are you that decay that was detected is the Higgs boson?
Because it behaves exactly as the theory predicted it would. That's the point. For instance, before declaring that the peak that was seen in the distribution of the invariant mass, for instance, in the two photons decay channel, was indeed compatible with being the Higgs boson, and we had to wait until we had accumulated enough data to compute the probability that peak that we saw, two experiments saw a peak in the same distribution in the same region, that was due to chance, because you have that things fluctuate, you have statistical errors in the measurements, and when you measure things, you have that you can have random fluctuations, but then they happen with a certain probability, and you can compute by how high were the chances that this would be a random fluctuation and not a real signal of something real happening. And there are rules in the community, and you announce the discovery when this probability that is due to random fluctuation is something like 1 in a million, less than 1 in a million, or even less than that. There's the equivalent of 5 sigma out of a Gaussian distribution, and so there are statistical conventions about this. And then, of course, we said that this was evidence because we knew that we had the theory predicted that it would behave like this and decay to photons and so on. And then we have made a lot of other measurements in decay of the same particle, which is, you have something which has a mass of 125 GeV that decays to a couple of other particles, and we have measured. We have measured. Sorry, the rate of these decays, and there are plots I can show you where these rates. So, saying that the probability of this particle, whatever it is, to decay to another pair of particles, is actually the amplitude, what we call the amplitude of which gives rise to the probability of actually the thing actually happening, is proportional to the mass of the decay of the particle it decays to. So this is what we call the coupling of the decay products to the parent particle, and the coupling is proportional to the mass, as Higgs boson should do. So exactly what the theory predicts for it to do, it's showing to have done. We have measured the spin of the particle. It's supposed to be 0 spin. It's consistent with being a boson. So a boson with 0 and not with 1 or 2 spin, the value of the spin. So it's everything, all its properties are consistent, but we still need to measure more to be more convinced that this is the actual Higgs boson that is that in the theory. For the moment, every measurement is perfectly consistent with what is predicted.
Okay, thank you for that, and for your honesty to say that it could be something else. But one final question, I'm sure, and I gotta go. I'm sure there's other people that want to get in. Isn't the Higgs boson supposed to be a field? And if so, how are they smashing a field? How are they the particles that they're smashing, right? What does that have to do with the field? I mean, it's kind of confusing for a layman such as myself.
Yeah. I know, of course it is, and that's not none of your fault, of course, because again, these are very difficult things, and it's not easy to explain them. And if you have to explain them to lay people, then you have to use analogies, and these analogies are analogies. They're not the real thing. So the real thing is the mathematics, which is complex of these things, and so it's very hard to turn them into analogies. And when you hear the analogy, you might have a gist of what it is, but not you cannot claim that you have understood. I'm not thinking that you are doing, but but some people are.
But hold on, let me interrupt you for a second, please. You're saying now you're saying it's hard to understand because it's a mathematical formula, but you're actually doing something physical, smashing particles together. Yes. So I mean, isn't that kind of like a double speak? With all due respect, not to you, to the theory.
No. The theory is it's quantum field theory, and it all, if you want, it all originated at the beginning of the 20th century with quantum mechanics, which and even with light itself, which can be viewed as a wave, so as a field. In classical mechanics, light is a field, is the propagation of electromagnetic. But in quantum mechanics, you have that at a quantum level, you have the light can also be described as particles, photons. And so quantum mechanics has this so-called duality or complementarity of descriptions of things of objects, fundamental objects being described depending on the kind of experiments that you do as waves or particles. And you have these two are both valid, and you know where to apply the description properly. But this is true. So that was evolved into quantum field theory in the mid 20th century, Feynman and others, and this describes every fundamental particle as a field. So it's not just the Higgs boson. The electron is a field. The quarks are fields. Neutrinos are fields. Light, W bosons, which are and Z bosons, which are the mediators of weak force, the gluons. Every fundamental particle is described by fields, and it's always been said as an analogy that the particles are sort of ripples or perturbation in the field.
So yes, I'm aware of that. Yes, that's why I brought it up. Like, which is it? Yeah. Like, they show like a field, like a sea of water, let's say, and then you see a spike, and then they say, "Oh, there's the particle," right? I mean, it's like a double. It's like two things in one. Yeah,
it's sort of true. It's a double speak, but it's not a double speak in the sense that, in a bad sense. It's intrinsic. As far as we know, it's intrinsic to nature. It's intrinsic, at least to the quantum description of things, that you have this dual description of particles, which are both described as fields and as particles. But they're described as fields in quantum field theory. But then, when you do the actual experiments, you treat them as particles most of the times. But it's not something that would require hours. But it's something that's fascinating because for instance, I always tell the students before we go to CERN every year to see experiments. They are second-year students, so they've not studied quantum mechanics yet, and so they're not familiar with this. And so I tell them that what we do in experimental particle physics is to treat fundamental particles as little balls. And indeed, there are people who mock us for this. As we seem to forget everything about quantum. It's not true in reality, because when you make, so we see, for instance, an electron or a pion, which is a charged meson, or a proton, we see them. We actually track them through our detectors as following a very well-defined trajectory. So as if it was a real ball moving across the table. But the point is that we can treat them. We know that we can treat them like that, even theoretically. It's not a contradiction with the quantum field. But there are things that are intrinsic and inherently quantum that not disappear. For instance, the fact that when two particles collide, the angle, for instance, at which the products of the interaction or of the decay come out is completely determined by a probabilistic law, and the probabilistic law is dictated by the interaction of these fields. So it's you make the calculation of what the distribution of the outcoming angles will be based on the theory which treats the particles as fields, and then you see, say, the little balls coming out, and the little balls coming out, you make histograms of at what angle they came out, and you see that they fit the distribution, the probabilistic distribution that was computed by the theory, and there are other aspects which are inherently quantum and cannot be treated as classical little balls, which are, for instance, neutrino oscillations. This is another kind of neutral meson oscillations, which is really something that is really impressive. Particles, for instance, the neutral K meson or neutral B meson, these particles change their identity while they travel. So it's like something changing their color, changing their name, changing their sex, so now that is their gender. Now that I always make this kind of joke. It's like
what a surprise!
Yeah, but it's not that. Of course, they change from particles to antiparticles along the way, and you can measure this kind of oscillations. you measure it, it's really impressive. It's something that is not explained classically. It's perfectly explained quantistically, and it's beautiful. There are plots from some experiments from my colleagues which are really, really impressive about this. And you have neutrino oscillations that they were not expected, but they were found, which implied that neutrinos had masses. We thought, when I was a student, I was taught that neutrinos didn't have mass. Now we know that it has to have some very tiny mass, but it has to have, because otherwise they wouldn't be able to oscillate one to another. So they're changing their identities as they travel along.
Well,
this is
very.
Excuse me.
Yeah, very interesting.
Isn't
and
this what you asked?
I want to thank you. Just give me a second, guys. I gotta leave. I want to thank the professor. Thank you for the convo. It was very interesting. Thank you for your time. And of course, I don't buy a lot of this stuff, and of course, I don't understand a lot of it. But thank you for your explanation and for being honest. And I hope we can talk some other time.
Okay, thank you.
I would just like to point out that didn't he say earlier that if you have a mathematical like equation to prove something, that you need an experiment, and like how is this not exactly what he was asking for as evidence?
Yeah, it is. It is. So indeed, you have a theory that predicts that the Higgs boson has such and such properties, and then you would detect it this in this way, and was searched for 40 years, and then it was found eventually. When I graduated in 1987, we were on the verge of starting the LEP experiments, which started in 1989. So my graduation thesis was about some search at the some measurements at the LEP experiment, LEP collider. But the big fuss was that people were convinced were searching for the Higgs boson at the LEP, which was an accelerator which was active from 1989 to 2000. So it ran for 11 years, and we didn't find the Higgs, and we didn't find the.
Was that due to the energy of the lab?
Yeah, the energy was too low, because the point was that the theory predicted that there would be this particle, this boson, but it didn't predict what mass it would have. So we just have to search for it, or determine it by indirect measurements, which is another very stunning property of the quantum physics. You can infer the properties of some particles even without seeing them, but just their indirect influence on other measurements. And you know how to do that calculation. And for instance, this is what happened with the top quark. The top quark was too heavy for the LEP collider to find, because it was too heavy, 172 GeV, the mass. We couldn't do that. Our energy was too low. But we made other measurements, and other measurements, the result of those were influenced by the value of the mass of the top quark, because it entered the theoretical predictions. And therefore we knew, by making precision measurements, that we sort of narrowed down the interval of possible values for the masses of the top quark, and we told them to the Tevatron collider, which was in the Fermilab in the United States, and then they went and looked at that energy, and they found it. So we told them where it was via indirect measurements, and they discovered it. 172 GeV. So that was also very, very, very impressive. So yeah, we didn't find either the Higgs or the top quarks, at lab because the energy was too low. But we made other precision measurements, and which helped, for instance, find the top, which helped exclude the Higgs. And we knew that at the end of lab that the Higgs had to be light. We couldn't be too heavy.
So you sort of predicted the top quark based on the effects it had on all other particles, even though you didn't detect it. Is that my
exactly? Yeah, that's one of the most impressive things. Yes, I showed in my particle physics course to the students. It's not that I made the plot, but it's very impressive.
Fascinating. Do you know anything about the neutrino experiment from CERN to San Grasso in Italy?
Gran Sasso, yes. Yes, I know because in 2011 there was this false scoop.
Traveling faster than light kind of thing that came up.
Yeah, and then it wasn't true, and everybody was overexcited about that, and it wasn't true because people had leaked. There was some. People said, well, some rumors will never be proven, but it was some rumors saying that one scientist who's now dead, an old senior scientist who was Italian scientist, who was one of the founders of the Gran Sasso laboratories, he wanted, say, a Nobel Prize for himself, so he wanted to take the merit of it, and so as soon as he heard that there was something new, he told the press. So he leaked the news before it was checked, before it was thoroughly checked. Because if I had the time to check it, to cross-check it, many times they would have found the problem. But indeed, it was leaked, when the press gave them, the Einstein is contradicted. You have things that go faster than light and so on, and wow, discovery of the century and so on. So they had to go out. At that point, the bosses of the experiment had to come out to the press and say, yes, we have this measurement. And I saw the seminar. They gave a seminar at CERN. I saw it in live. I wasn't there in person, but I saw it streaming, and yeah. It was a big deal, and then, of course, when a few months later it turned out that it was not true, then it was not a good situation for the person.
One important question remains: does CERN cause the Mandela effect?
No.
Why would people say that?
Because I don't even know what it is, but I know that at some point there was this sort of hype about this, and they even involved John Ellis, who is a British theoretical physicist. He's very old now. But I see last time I was at CERN, I saw him, and he's probably just out of British humor. He just humored them and said, yes, it's true, something like this, but it was just a mockery. They made some video or some press, I don't know, it was documentary, and it was a mock documentary. Of course it was something that was made up in order to make fun of the conspiracy theorists. But yeah. I know for certain that John Ellis agreed to say what he said. I don't even know what, just as a joke.
So when neutrinos hit an atom, does it change its energy, or how does that work?
Well, normally neutrinos, the point in neutrinos is that the probability of it actually hitting, in the sense that we normally give to the word hitting any particle is very, very low, the probability. So they basically go through matter undisturbed. We are traversed by a number of neutrinos. I don't remember how many, but we are really traversed every second by hundreds, if not thousands, of neutrinos from the sun, and basically mainly. And but so it's very basically you don't. If they didn't interact at all with matter, if we didn't, then they would be impossible to see. If something doesn't have any effect at all on other matter, then you don't see it. You cannot measure.
Is it measured by this? That's what's it called? Cherenkov radiation in these detectors?
No, because Cherenkov radiation. I know what you're saying. Yeah, so yes and no, because Cherenkov radiation is something that measures the it measures the velocity of charged particles in water, for instance. But the big neutrino detectors, such as Super Kamiokande in Japan, they are basically enormous water tanks, and they're lined. They're a gigantic cylinder. There are pictures that with boats floating in the water there. They're gigantic cylinders filled with water, and the surface, the internal surface, is lined with photomultipliers, which means that they are photon detectors. They're light detectors. And what they want to see, the signal, is that at some point light comes out of nowhere from the water, and in rings especially, which is a signature of Cherenkov radiation. Cherenkov radiation is basically the equivalent of a sonic boom, but with light instead of sound, for a particle that goes faster than light in a medium, for instance. So if for instance an electron moves faster than light in water does not move at the speed of light. It moves at the speed of light divided by 1.33. So if an electron instead is very relativistic and it moves at nearly the speed of light, it moves faster than light in water, and so light in water makes the equivalent of a sound shock, the same that you hear with supersonic jets, and you have and it forms a light cone, and this is a Cherenkov cone, and this is it actually measures the amplitude of this cone. If you detect it, measures the velocity of the electron, for instance, but it has to be a charged particle. The point is that when a neutrino of the electron type hits an electron, it may scatter it. So the electron is kicked out of the atom, or it may turn to an electron itself, and then, for instance, change the a proton to a neutron, or something like that, or a neutron to a proton from an atom. So if it hits, for instance, if a neutrino, an electron neutrino hits a neutron from a nucleus, then it can turn the neutron to a proton, and it neutrino, Y should be male, but the neutrino, maybe because it ends by O, it's a male in Italian, it's masculine. So the neutrino will turn into an electron, and at the same time turn the neutron to a proton. And so the electron is then very relativistic and it's charged, so it will produce this Cherenkov light, and you see that. But that process is very, 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 very rare, and the probability is very, very, very low. But that's the way you detect neutrinos.
So how do you measure the energy of the neutrino?
you can infer it from the velocity of the neutron. Sorry, from the velocity of the electron, but it's not. You miss. If you would need to know the direction of the incoming direction of the neutrino. So it depends. It depends on the kinematic of the experiment. If, for instance, it's the CERN Gran Sasso experiment, then we're sending a beam of neutrinos, and on neutrinos of a particular type, which is the muon neutrinos, and then so it would mean that in that case, when a muon neutrino hits a neutron, it would turn the neutron to a proton, but then the muon neutrino would turn to a muon, not an electron. And then, but that you can measure the energy because you can measure the direction of the outcoming muon. You knew the direction of the incoming neutrinos because they were a beam from CERN. Instead, in experiments like Super Kamiokande and so on, you don't really know in general where the neutrino came from, unless, for instance, it was from a supernova. If there's a supernova, which is a source of neutrinos that you expect, then you know where the supernova is in the sky, so you know where the neutrinos are coming from. Or if it's solar neutrinos, they come from the sun, so you know the direction. But if it's other, like atmospheric neutrinos coming from cosmic rays and so on, so then you don't know the original direction, and so probably you cannot reconstruct the energy of the original neutrino.
And these neutrinos have different energies, don't they?
Yeah, it depends. Usually, yes, they do have different energies.
Because I think quite recently I think it was one of the space telescopes of some sort, which measured the highest energy particle ever.
Well, of course, if it reacts, if you have a neutrino that produces an electron because it hit a neutron, for instance, and then you only measure the electron, but the electron has a very high energy, then of course the initial energy of the neutrino must be higher than that. So you have a sort of lower limit to the neutrino energy. And sometimes there are other kinematic variables that allow you to actually reconstruct the energy or place some more stringent limits on the energy. Say it was certainly higher than that.
Yeah, because the other day I brought up this Sangrasso, CERN Sangrasso.
Gran Sasso.
Yeah. Yeah, because from my understanding, that the beam has like a downward, it's aimed slightly downward to hit the detector at Sangrasso. Yeah.
Sorry, it's gran. Gran means big. Sasso meaning stone. It's big means big.
Yeah, it's stone. Inside a mountain, isn't it? Yeah.
Yeah, it's a mountain. No, because grasso means fat.
Oh, so okay.
That's why I'm giggling if you say San Grasso, because it means like something in Italian means like saint fat. So
no, well, it's a nice description of a big mountain, though.
Yeah, saint fat. Yes. Yeah. Anyway, yeah. The point is that I frequently bring it up with flat earthers because yeah, the beam, the neutrino beam, was sent from CERN with a 5.3, I guess, or 5.6 percent angle relative to local horizontal. So it was sent downwards because it had to reach Gran Sasso, which is at 7,000 kilometers distance. So it needs, if you draw the chord in a circumference, the radius of the Earth, you see that is the angle, and you see that the maximum depth underground in between the 2 points on the surface is 11 kilometers down. So it's a big it went very deep inside the crust. And
and they did the same in the US as well, didn't they?
Yeah. The Dune experiment. They're still building it. Because they have East Coast to West Coast neutrino beam foreseen.
That long? Because the previous one was from, was it Minnesota or to, I can't remember how long it was.
Fermi Lab to Chicago did it to Minnesota.
Yeah, and now they're building they're designing a new one from, I don't remember if it's still Fermilab, but it's to SLAC or something like that. It's to California, if I remember correctly, but it's East Coast to West Coast. I can look it up, or you can.
Well, thank you very much.
What about the neutrino detector in Antarctica?
Oh yes, there are neutrinos. Ice Cube, for instance, it's in Antarctica, and then those are yeah. Yeah, well, I know of one that is called Ice Cube, but maybe there's more than one.
And they're building the undersea one outside of Sicily as well, aren't they?
Outside of Sicily?
Yeah, in the sea, they're putting down a hell of a lot of detectors.
I don't remember. I don't know. I don't know about this. Maybe I should.
They tried to measure the orbit and then found out you couldn't measure the orbit because you can't measure things free falling, which is what the orbit is doing, free falling. So they had to introduce relativity to make it all work with a Lorentz contraction. They did a little mixed drink session done.
I think that's where like a lot of flat earthers get a little mixed up, is they try and tie in everything to heliocentrism, when heliocentrism at the very baseline is just the Earth rotating around the sun and not the sun rotating around the Earth. Hello?
Did you respond to something I said, or?
Yeah.
Didn't sound like it.
Oh,
you can't measure things free falling. You can't measure things free falling. They went to measure the orbit. They had to come up with a way with, oh my God, how will we measure this thing going in a circular path? We can't measure it. We should have measured it according to Newton. And in comes relativity, mix in a little Lorentz contraction, and now you have your orbit working. Now you can explain an orbit where you couldn't be before, because like I said, under Newtonian mechanics, that should have been measurable.
Again, we're not talking about something that's measurable, Jeremy. We're talking about the physics of orbits. I'm not really sure like what you're missing here.
Newtonian mechanics does not work for the physics of orbits because there's no force there. You have to have something where there's no force, and you also have to not be able to measure it, which they can't measure the orbit.
What?
Not shocking, which isn't shocking because I don't think. What part did you not hear me? What I said? Are you just interrupting me with a what, or you really didn't?
No, I'm completely lost as to what the fuck you're babbling about, and I'm trying to say like what, so that you can actually more emphasize what I'm saying what to.
I don't know what you're saying. What part don't you understand?
The entire statement that you're trying to babble out, Jeremy. That's why I said what like 3 different times.
I'm speaking very coherently. I'm sure everyone else can understand exactly what I'm saying.
I don't think a single other person can actually steel man what the fuck you just said.
Can anyone steel man me?
I can try it.
No.
What?
I can try saying that you can't measure something orbiting, so they needed Einstein to come in and save the day because that's as far as I got.
There you go.
Because you need Einstein. Because you need Einstein.
Because under general relativity, that's how you can get something moving in an accelerated path in orbit, but not measure it. Under Newtonian mechanics, you should have been able to measure it. You can't have an orbit with Newtonian mechanics.
Are you saying we?
This is why I said what, Jeremy? Not a single person in here could fully steel man your argument. You weren't being coherent. I'm not being rude. You're just not speaking clearly.
I think the argument is they need Einstein to muddy the water. Without Einstein, they can't muddy the water, so they have to bring in Einstein for everything. And if that doesn't work, then bring in dark matter.
No, they had to bring in Einstein so they could explain an orbit. That's what they had to do.
No, they don't have to.
No, you. That's your rebuttal. No, you.
No, you are wrong about that. They didn't have to bring in Einstein.
They literally did. They couldn't explain the orbit without Einstein. It didn't make sense in Newtonian mechanics. I'm still talking. It didn't make sense in Newtonian mechanics because it would have been measurable. They didn't measure it, so they freaked out. Like, oh my God, nobody really even wanted Einstein because it was just total. Hold on, just go on mute, dude. Just go on mute for a long time. You guys be mumbling the whole way through people all the time. I don't even remember where I was. Orbits don't work in Newtonian mechanics, so.
But again, that's not true.
Yeah, see, I was counseling people against talk about Einstein, and here I am. I don't believe in Einstein. Einstein's fake.
Nobody cares, dude. It's a topic we talk about sometimes. Nobody gives a fuck. You're not the main character here.
Yeah, I think it's a dishonest way of muddying the water, Jeremy. And it's done enough that I think I'm gonna see how often it's done and in what context it's done. I think all you're trying to do is muddy the water.
Nobody cares.
The topics are why the sun orbits, or why we orbit the sun, and why the moon orbits us, and how that happens, and what the moon is, what the sun is, what the planets are. Those are the general topics. Those are the things that are in contention. Is Earth spinning? What causes things to fall? Those are the things we're talking about. But as soon as we start getting close to the truth, you go off on dark matter, dark energy, Einstein, all the rest of it.
You guys acted like you could just use Newton for the orbits. I'm letting you know you can't use Newton for the orbits because an orbit would have been measurable under Newtonian mechanics. And guess what they can't do? They can't measure an orbit. Maybe that was unclear and Chief needs me to repeat it again.
Well, again, you're still misinterpreting Michelson-Morley, which I don't understand how that could be if you've been talking about it for over a decade, Jeremy. But like maybe somebody actually needs to sit down and read it to you. Because I've been telling you that you've been interpreting Michelson-Morley. You keep talking about orbits. It had nothing to do with Earth's orbit. It had to do with its rotation. It accounted for Earth's rotation. It knew that Earth was rotating. It had rotating in its math. So I'm not sure what you're talking about.
What do you mean by not being able to measure orbits?
Well, again, Michelson-Morley had nothing to do with orbit.
Something free falling. It had nothing to do with it, but the tool they used should have been able to measure it. You can't measure yourself free falling if you're on the free falling object, right?
No. Michelson-Morley's experiment would not have been.
You can measure yourself free falling if you're on a free falling object?
Michelson-Morley's experiment, their tools that they were using were not calibrated enough to be able to detect orbits.
So
they weren't detecting.
We literally went over this last time. They were way sensitive enough. Yeah, they weren't. Funny.
No, they were not sensitive enough. Again, you're misinterpreting. Again, it had nothing to do with orbit. Nothing in their equations had to do with orbit. It was all about Earth's rotation. You know that thing it does like every 24 hours rather than every 365 and a quarter day? Can you continue to be wrong, Jeremy, or does somebody need to bash in the fucking math into your head again?
I can help here. Mars's orbit around the sun was precisely calculated and proven to be an ellipse by Johannes Kepler in 1609. Tell me what that has to do with Einstein.
There you go.
Thank you very much.
And again, anybody that's able to just look at the equipment and look at the claims by Michelson and Morley, both claim that they had nothing to do with orbit around the sun. It had to do with rotation. So every time Jeremy's been sitting here lying about detecting Earth orbit, it had nothing to do with Earth orbit. It had everything to do with rotation. Their equipment was not. Their equipment was not precise enough to detect any orbit. It was looking for rotation through the aether. They predicted aether drag. They got no aether drag.
My theory is that when Einstein, etc., is brought up, it's a red herring. Now that you know that the orbit of Mars was measured and observed, or observed and measured by Kepler, I think if you continue to say that we couldn't measure orbits without Einstein, I think that's a sign that you are not being honest in this conversation, Jeremy.
Dude, shut the fuck. Nobody cares if you think I'm being dishonest or not. You just keep saying it over and over again, dude. Shut up.
Well, there's a difference between being dishonest, Jeremy, and being wrong. I genuinely think that you're just horribly wrong.
But what's the point under debate?
Whether they needed Einstein to predict orbits or to measure orbits. Jeremy's contention is Einstein was necessary to come and save the day because you can't measure orbits using Newtonian physics.
But Michelson-Morley wasn't trying to detect orbits. They were trying to determine like how far off the lasers would be during the course of rotation. Earth's days, not Earth's years.
No, I think it was years. I think it was orbit because they were trying to do. I could be wrong, but they were trying to. That's why they did it over the course of a full year.
No, it was throughout the days. And like even in their writings, they predicted like several scenarios. Either the Earth is not moving, and the Earth the aether flows through the Earth and changes directions throughout the entire day, which they saw as ludicrous. or the Earth rotated throughout the course of a day through the ether, like through like a still like unmoving ether, which the theory that they
I'm
went
reading
with.
this though. I'm reading this. Yes, the Michelson-Morley experiment. All right, fine. You're all right.
But I don't want to hear what you have to say, Jeremy.
Oh, you just read that I was right.
No, you're not right. The Michelson-Morley experiment was trying to measure the motion of the Earth with respect to the ether due to revolution around the sun, the orbital motion. It's not
And it was sensitive.
rotation.
Let me just read this real quick. I don't know why you're going to welcome Danny Faulkner, but let me just read this real quick. Yes, the Michelson-Morley experiment was more than sensitive enough to detect Earth's orbital velocity. There you go. You were wrong. You said it wasn't sensitive enough. It is though.
But it wasn't.
I just Googled it.
Where are you reading that it was?
And Dr. Faulkner, the PhD astronomer, is telling you that you're wrong.
And Earth's velocity.
Can you post me the results?
Earth's velocity around the sun is a lot greater than its rotational velocity. By a lot.
Go ahead.
Yeah. But if you look at their theories within their tools, it had everything to do with rotation.
A few decades later, Michelson, Gale, and Pearson did indeed measure the motion of the Earth's rotation with a much more sensitive interferometer. Again, you're incorrect. Jeremy is right. I hate to admit it about this one thing. It was an attempt to measure the Earth's motion due to the Earth's orbit around the sun.
He said rotation.
In astronomy, we distinguish between rotation and revolution. Rotation is a circular motion around an axis passing through the center of the body. Revolution is circular motion around an axis outside the body. The Earth revolves once a year and rotates once a day.
You just said it was measuring rotation. So which is it?
He said orbit.
Yeah, dude, you said rotation.
It's revolution.
Orbit would be a revolution.
We can pull the paper up. I think I got it here somewhere.
Again, Michelson-Morley experiment 1887 was attempting to measure the Earth's motion with respect to the ether due to its orbit around the sun.
So they acknowledged
so revolution, not rotation. Revolution, not rotation.
Yeah, but he said rotation.
That's a revolution, not a rotation, the sun.
So they did detect rotation then, and ours should say revolution. So why is Jeremy saying that they didn't?
They measured the rotation of the Earth decades later with a more sensitive interferometer. We're talking about the 1887 experiment that was attempting to measure, again, motion of the Earth with respect to the ether due to the Earth's orbital motion around the sun. It's revolution, not its rotation.
Okay. So they did detect it then.
Not in 1887. They got a no result.
Okay, yeah,
they did with Michelson-Morley Gale.
And the Michelson-Gale-Pearson experiment decades later was a similar experiment done to measure rotation, and they got a positive result for that one. That's because there's a fundamental difference between rotational motion and revolution.
Yeah, one's a lot easier to detect because it's faster. The other one, I should say, it's change on its axis is faster.
No, that's not it. No, it's slower. It's actually slower. The difference.
He's getting everything wrong, Faulkner. I don't know what to tell you.
It's like
hold on. How is the course of a day? How is the course of rotation over the course of a day slower on its axis than over the course of a year? Can you
you should turn on motion.
I can explain it.
The difference between rotation and revolution, Chief.
Well, no.
How about let Dr. Faulkner explain it because he brought it up?
24 hours versus like one rotation every 365 days.
How about we let Dr. Faulkner explain it?
Yeah, let Danny. I cut him off. My bad, Danny. Sorry.
The maximum rotation speed of the Earth is a little over 1,000 miles per hour. The revolution speed is on the order of 18 miles per second. So it's a several orders of magnitude larger revolution is than rotation if you're talking about the linear motion involved.
But again, it's not detecting linear motion; it's detecting rotation.
I can
no,
give
it's detecting linear motion. It's not looking at rotation.
No,
it's you couldn't be more wrong about it. I don't think you heard all what I said about rotation and revolution.
It detects shifting on the X or the Z-axis.
Yeah. No. The original one is not the Z-axis, is it? The original one I think is the X-axis.
It's neither.
Whichever axis it's detecting shifting on the axis.
Yeah, but exactly. You say on the axis, but there's multiple axes. So which one did they check? And that was my response. I was going to give adding more to that.
The original experiment that wasn't about any Earth axis. It wasn't about that. It was about
an axis has to be
orbital velocity, 66,000.
But the point is,
orbit at 66,000, whatever, 666.6666 miles per hour, whatever people like to say, 66,000.
Okay, but the main point is though, under Newtonian mechanics, if you're accelerating, you should be able to measure that. right? That should be force F equals ma. These orbits in free falling situations, there's no force there, so you can't measure them.
Yeah, there's gravity.
Yeah, but that's not what they were trying to measure.
Accelerate. Hold on.
They weren't trying to measure that though. They weren't trying to measure force. They were trying to measure a displacement against what they assumed was a stationary ether.
I know, but I'm telling you, you can't. If you have acceleration according to Newton, you should be able to measure it. But you don't have proper. Yes, but you can't do that with an orbit because there's no proper acceleration. It's just coordinate acceleration.
You can measure velocity as well.
It's centripetal acceleration.
That's what I'm telling you. You can't have an orbit with just Newtonian mechanics. It doesn't work.
Yeah, I don't understand what you're saying there. Of course you do. There's a centripetal force acting, and it gives you orbital motion. Newtonian mechanics explains this beautifully. I don't know
Why
what
do
you're
you
on
guys keep
about.
talking about Newtonian mechanics?
Why not?
It's a different. It doesn't matter if there are use cases where the results between relativity and Newtonian mechanics are so similar where you could use one or the other. The globe model is relativity. Newtonian mechanics is the old school. Get that out of your fucking mouths.
No,
if you're gonna test it to break it, you're gonna use relativity.
No, it's not old school, brother. Newtonian
The
mechanics
entire
is normal.
argument revolves around the need of, like, was it a Einsteinian?
No. The other guy
wow.
said it's not old school. What are you talking about? So
Why the fuck are you sparking out over me for? Can you shut up?
K-Breaker,
relax,
calm down.
K-Breaker.
What the hell?
The argument revolves around, like, one side claiming that it is not required for Einsteinian equations to have the Earth rotate around the sun, the quote-unquote heliocentric model. The other side is claiming that no. That is the entire purpose of this argument.
No, I'm telling you, Newtonian mechanics can't work with an orbit because in Newtonian mechanics, you should be able to measure the orbit from being on the thing. We're on the thing, we can't measure it. Just like a free fall, you can't measure yourself free falling. You guys
Is
say.
Newtonian physics is Newtonian physics capable of having the Earth rotate around the sun?
Yes, but we would measure it though. It would be measurable. Michelson-Morley would have measured it.
We're going in a circle here. Michelson-Morley was attempting to measure.
No. It depends on what Michelson.
Robert, Danny was speaking.
Danny was talking already.
Michelson-Morley was an attempt to measure the velocity of the Earth with respect to the ether. That's simple as that. And we keep going in circles on this, but that's what it was trying to do. It failed to do
They did an
it.
experiment, and they were testing which particular axis in their experiment of movement.
Yeah, they got a null result because there is no ether.
Which particular axis?
Okay, they also got a null result for the orbit because you can't. It
Because
doesn't
they were
have
not measuring.
proper.
You'd say
it doesn't have proper acceleration.
I'll answer it there. It's an axis. Oh, sorry, Jeremy, go ahead.
Which axis? X-axis.
It's an axis relative to the ecliptic.
Which axis is that? X-axis.
Ecliptic. No, it's
Which
an ecliptic
axis
plane.
is that?
The ecliptic plane. It does. I don't know what axis it is.
Do you understand XYZ? Which axis is
I
that?
do.
Gatebreaker, calm yourself. Calm yourself.
Pfinky, no. Excuse me. The correct route and behavior is to figure out which axis it is, and not to repeat the non-axis.
Just stop shouting.
No, I won't.
Daybreaker. The ecliptic has two axes on it. Let's say.
So which axis is it?
Well, the Earth goes and moves through all of them, so it's at different times of the experiment. It would be considered a different point of the axis.
Yeah. Again, Michelson-Morley's experiment. Michelson-Morley's experiment was not designed to detect Earth's orbit. It was solely designed to detect the shift in the speed of light caused by aether drag. There was no aether drag. So again, whenever Jeremy says they didn't detect Earth's orbit, he's essentially lying because that's not what they were trying to do. That's not what the machines were designed to do.
I'm not lying.
I mean, I guess it's technically true on a really weird technicality.
No, it's not technically true. That's not what we're talking about. It was they made an assumption. They made an assumption. They made an assumption that there was ether. It was an assumption. There was no ether.
Yeah, I'm making a dumb point. I'm saying if I do an experiment to show that water boils at 100 degrees, my experiment doesn't show how light bends through plastic.
So they failed to detect the ether from the lack of what they were expecting from their measurements on what axis?
What? One of their assumptions was that
Daybreaker, just Google it.
Google which axis. The correct answer is you don't know. Red Cloud doesn't know, and Pfinky definitely doesn't know. You guys don't fucking know. It is the X-axis. That is the answer.
No, it's not.
Yes, it is.
Actually, I think he's right.
Let's Google it.
Yeah.
Actually, I think he's right because that was
You're
like
gonna send it to me after you Google this, okay? Because you just
that was
wasted my time.
because there was a two. You're right. There was a 2 on the X-axis and the Z-axis, right? and they were looking for the shift on the x-axis because that would have been the direction of travel.
Thank you, Chief,
through
for
like
being honest,
to the supposed
smart,
answer.
and higher IQ than Pfinky.
So yeah, but like the thing is like the device itself was not designed to detect Earth's orbit or Earth's rotation. It was designed specifically to detect a change in the speed of light through one of the tubes. So anytime Jeremy tries to say, "Oh, they didn't detect any orbit, they couldn't find orbit," well, they weren't looking for orbit. They knew that there was
counter? What's the potential counter to that experiment right there in the results?
There is no counter. There's no counter.
Anyone know?
There's no counter.
Anyone know?
There's no counter. There's no counter,
Anyone
brother.
know? Okay, Robert says there is no counter. Anyone else?
I would like to.
What if?
I don't know what a counter is.
What if they were to rotate the instrument 90 degrees and have it essentially measuring the z-axis primarily? Are the results the same? No, they're not. You guys have never heard of this before?
Danny, I'm dying to hear Danny. Let Danny answer the question.
Never heard this before? I'm going to post a link to the experiment. Get fucked. Don't try to correct me.
I'm reading the experiment right now. There's no. I'm curious Danny's take on which axis they were measuring. How he would answer that.
They were measuring the axis. They were just measuring it along an axis.
Yes, the movement is that.
Yes.
Yes. Right, I'm curious what Danny would say.
In the Michelson-Morley experiment, they were measuring the difference in the speed in two different directions, perpendicular to one another in the plane of the Earth's orbit, one in the direction of the Earth's motion and one perpendicular to the Earth's motion. So when we say an axis, I don't know what you're talking about. There are actually two directions you're comparing.
Thank you. That was my
right.
point.
Yes. Remember.
Can I point out something real quick? I think that even if the ether existed, I still think they wouldn't have detected anything. It's like you try to measure your speed by measuring your speed relative to the airplane seat of the airplane that you're in.
What?
You're not.
Why, that's a perfect experiment. If you can demonstrate movement relative to your airplane seat, then you can definitely say that me and the airplane seat are not moving together.
But there is no difference between the airplane seat's movement and your movement. But the plane is still going 500 kilometers an hour or something.
Yeah, but the theory was that the ether was stationary and the Earth was moving through that stationary ether, and so they designed an experiment that should have been able to detect that change. The idea being that light was entrained in the ether, and so therefore on Earth you could set up an experiment to see a different behavior of light depending on which orientation you used.
Well, they actually had three theories as to how the ether behaved in relativity to the Earth. Two of which they tossed out because of how ludicrously dumb they were. One being that like the Earth was rotating around or orbiting around the sun, of course, but that the ether somehow always changed its path to perfectly be aligned with the Earth's movement. Like, let's say you don't detect wind when you're on your plane because the wind is always shifting to be like at your tail or something, regardless of which way you turn. That was one of their theories that they immediately tossed out because it was ludicrous. The other theory was, the Earth is stationary, but the luminiferous ether is always like flowing in a way where it's constantly changing directions to like essentially mimic an orbit, which they also tossed out as ludicrous. And the other one that made the most sense was that Earth was rotating around or orbiting around the sun, and the ether would be stationary.
Okay, but without this, no, Robert, no. Without even let's say they debunked the ether and there was no ether. Their tool should have measured the orbit. It didn't measure the orbit. Can we get past that? You were already wrong. You were already wrong. You were already wrong that it was sensitive enough to detect the orbit. We've already come to the conclusion that it was sensitive enough to detect the orbit. Can we get past the next point?
The Michelson-Morley experiment measured no detectable effect of Earth's orbital velocity on the speed of light. They were not measuring Earth's orbit itself. Interesting, Jeremy. It's weird how
we know they weren't trying to measure. We know they weren't trying to measure the orbit. However, since there was no ether, they should have measured the orbit. They didn't measure the orbit. They had to invoke Lorentz.
No, why would they measure
you guys all act like they didn't have to invoke Lorentz contraction and relativity right after this to fix it.
Cause and effect, Jeremy. They were looking for the orbit. Period. End of story. It's not every experiment. It's not every experiment results in something else different from what you were looking for. It's not every experiment does that. There are some experiments that have done that, but this particular experiment that Michelson-Morley were doing did not result in any mistake and say, "Oh wow, look, we detected the orbit of the Earth around the sun." It did not result in that. This particular experiment had too little variables involved. They were looking specifically for this ether nonsense. It didn't exist. Period.
The original experiment failed to test on the z-axis. I have an experiment that tests on the z-axis that detects the fucking shift. I don't know if it's real or not, but
well, again, so they did not have. They did not have tools that would have it would have been sensitive enough if they had it on the correct axis to detect Earth's rotation.
It was sensitive enough.
Okay, so I'm going to repeat myself again. They did not have it aligned correctly to detect Earth's rotation or its orbit.
No, it's not that.
It was not on the right.
They were just not looking for that. They're looking for changes in motion because of the wave. The definition of wave is that you need a medium in which to travel. Light itself does not need a medium. That's the issue. Light doesn't need a medium.
It was not something that they were. It was not something that they were measuring or recording with the device.
When Michelson and Morley confirmed that when they couldn't find the ether, what they have done is basically said, look, light does not need a medium to travel. And that is how Einstein's theories then started to make real sense, right? When he came along, he's like, okay, if light doesn't need a medium, then wow, check this out, guys. Gravitational lensing, black holes exist, this and that. And he was 100% correct.
Okay, you're just wrong again, Chief. They rotated it in every axis. They definitely would have measured the orbit. You just keep getting everything about this wrong.
I'm literally reading it here, Jeremy. You're just being stupid. I'm going to read it to you again. It is sensitive enough to detect the expected effects, but the key is that they weren't trying to detect Earth's orbit directly. They were trying to detect the effects of Earth's orbital velocity should have had on light if an ether existed. Here's an important distinction. What they expected. Earth moves around the sun at about 30 kilometers per second. If the light traveling through the stationary ether, then Earth's motion should create an apparent ether wind. Michelson and Morley expected that light traveling in the direction of Earth's motion should have a slight different effective travel time. Light traveling perpendicular to the motion would have a different travel time. Rotating the interferometer would therefore cause the interferometer fringe to shift.
Yes.
So again,
yeah, but the only way they wouldn't have measured the rotation is if they had the apparatus going perpendicular to the orbit, and they did not have it. They did not have it going perpendicular to the orbit. They might have at one point, but they rotated it multiple times throughout this. It was on a thing. They already accounted for that and knew they were going to have to move it in different directions. So the thing you're saying is just not true.
The machine. I'm reading it right here. The machine is the machine was. I'm reading it right here. Ding dong. It was already calibrated to account for Earth's orbit. That's why they weren't trying to detect it. Dumb fuck.
It wasn't okay. First of all, it's not called names. Second of all, it wasn't already calibrated for Earth's orbit. They should have been able to measure it and get a bigger fringe shift. They got essentially a zero fringe shift with any error of margins. You're just wrong.
Jeremy, which axes did the original experiment that you're talking about test?
They had it rotating. They had it rotating. So they would do it one way and then rotate it, do it another way, rotate. They had this thing. They knew that they wanted to rotate it so they could check for this.
They didn't. It wasn't on an axis. It wasn't on an axis. Danny Faulkner already corrected you, Gatebreaker.
Huh?
They weren't testing it on one or the other axis. Like Faulkner already corrected you. No, you're misunderstand what the.
I'm not talking about the orbital thing like you guys are. I'm talking about the ether argument.
So yes, the experiment was specifically designed to be sensitive to the expected effects of Earth's orbital motion, but it wasn't a device for independently determining Earth's orbital velocity. Interesting. Would you like to repeat how fucking wrong you were, Jeremy?
Because you can't measure it. Because it doesn't have proper acceleration, which is what it would have in Newton's F equals ma category.
So yes, the experiment was specifically designed to be sensitive to the expected effects of Earth's orbital motion, but it wasn't a device for independently determining Earth's orbital velocity. Do I need to repeat it a third time to you, Jeremy?
Can you tell me what that means?
It would have been able to detect it. They would have picked up a bigger fringe shift if we were orbiting, given there was no ether. They should have picked up a fringe shift from the orbit. It was sensitive enough to detect the fringe shift from the orbit. You already got that wrong. And they did check every axis and they did not measure the orbit. They literally had to bring in Lorentz and Einstein later on to fix this because this was a serious problem in physics. I don't know if you knew that or not.
So yes, the experiment was specifically designed to be sensitive to the expected effects of Earth's orbital motion, but it wasn't a device for independently determining Earth's orbital velocity. I'll repeat it again for you, Jeremy.
This is wrong. This is wrong.
I'm reading it right here.
They cut the machine. The machine was sensitive enough to detect it. They didn't detect an orbit. If this wasn't a problem, they wouldn't have brought Lorentz in, I promise you, to bring in Lorentz contraction afterwards, which they did, and Einstein with relativity, because they had to fix the problem with Newtonian mechanics, given they should have been able to measure this with Newtonian mechanics. You can't measure free falling objects, right? If you're inside something that's free falling, are you guys fighting with me that you can measure this? You have no proper acceleration, according to you guys.
No, I don't think anybody's disagreeing.
Okay, so you can't measure. So you can't measure. Hold on, let me just follow through with this, so we're not fighting each other the whole time to get our points across. So you can't measure it. We're on the free falling object, Earth. You can't measure it. They didn't measure it. They had to bring in Lorentz and Einstein later to fix it. Einstein fixed it. Oh,
Well,
it's not
Lorentz
actually,
fixed-
it's moving in a geodesic, which is a straight line in my geometry, and a whole bunch of Lorentz contraction shenanigans.
What do you think Lorentz fixed?
He fixed the problem of them not measuring a fringe shift.
No.
So did
By
Einstein.
By doing what? He did by doing what?
He did. I know. Chief gets every. This is Scrappy Doo's flat and destruction
Okay.
little brother.
Why is Lorentz contraction no longer a concept we use, Jeremy?
You get everything wrong, dude. You're
Hold
getting
on,
everything
Jared,
wrong, bro.
answer the question, Jerry. Fix.
I don't know it, Jeremy. So if you don't know it, I don't know it either.
Lorentz contract. I already answered it. Lorentz contraction fixed the fringe shift. Them not getting a fringe shift, which they should have got if we were orbiting.
It kept the stationary ether, luminiferous ether concept alive by saying that the arm shrunk. Lorentz was an ether guy. You realize that, right? He was an ether believer. All Einstein did is he took that same concept and he just said, well, we actually don't need the ether. It's like an extra thing that doesn't help.
Yes, Einstein was the cherry on the cake. Einstein was the cherry on the cake. Yes,
but
that's
it
what
all
I'm saying.
started
You
with
can't.
ether. It all started with the ether boys.
I know, but my whole point was you can't do this in Newtonian mechanics where you have F equals ma, because if that was true, you'd be able to measure the orbit because you'd be accelerating. You'd be able to measure that. It'd be measurable. You would have got a fringe shift under Newtonian dynamics.
I don't know if that's true. Like, you could be right, but I don't. You have to
I'm
look
right.
at what
I'm right. I've been right this whole time.
Size. Wait, hold on.
But you haven't. You've been wrong at just about
look
everything.
at the size of the
Laughably
orbit.
so.
So you look at a one AU orbit. You look at the orbital velocity. That will tell you the acceleration.